These lighting effects can be pretty dramatic, but for me, nothing can compare with the stunning beauty of laser light, which you can now see. We have two lasers coming up from the floor, a red krypton laser and a blue argon laser. And if you follow it up, you can see the spots of light appearing on the roof up there. Today's lecture is about what lasers are, how we make them, and what makes the quality of laser light so special. So we should start at the beginning. What is the word laser? You probably all know that it's an acronym. That is, it is made up of the first letters of several words. And the words are light, amplification by the stimulated emission of radiation. We learned in the first lecture about light. Radiation is just another word for light. So the device really should be called a laser or a razor to be consistent. The words we need to know about in order to understand the laser are therefore amplification and stimulated emission. Let's begin with the second, stimulated emission. We know that to create light, we have to make electronically excited states of atoms and molecules. And there are many ways of doing this. One that I showed you in the first lecture was simply by passing an electrical current through a gas. And here we can do that again for you. Notice that the color of light that we get out depends on what the gas is. Here we have neon. Here we have argon. Here we have nitrogen. And at the end, we just have neon again. So the color of light is very specific. The neon would appear somewhere in this part of the spectrum here, the argon somewhere in that region of the spectrum there. Now, if you want to change the color of an electrical discharge of that sort, you can do so by coating a tube with a phosphor. And we have a display here which illustrates the number of colors that you can get with these different phosphors. These are just ordinary domestic fluorescent light tubes, but they have a different colored phosphor coated in each one. If we switch them on now, I think you'll be able to see you can get a rather nice variety of colors there. These are not filters. These are not placed on the outside of the tube. This is a phosphor which is put on the inside of the tube and is creating that rather pretty display of light. So passing electric current is one way of creating light. There's another way of creating light, which we again saw in lecture 1, and that is by a chemical reaction. Now I need 4 people to help me with this. Who shall we have? We'll have you in the front. Would you like to take that and go and stand along the end? And someone on the end there, please. There's one for you. Let me give you a different color. Would you like to come? Now we ought to get a lady, perhaps. Yes, there we are. That will do. Now I just want you to stand in line, hold this, and then just do what I do. If you put your thumbs in the middle, like that, when I say go, I just want you to snap what's in the middle and then shake the contents, all right? Ready, steady, go. Shake them up. Now, what we've done is to mix 2 chemicals in there which have caused a chemical reaction to occur which has produced an excited state which is giving out light. So that's another way of us producing light. Now, I'm going to take these away from you as you go back to your seats. Thank you all very much, because you'll play with them all the way through, I'm sure. There we go. Now, can we hide those somewhere, please, Bryson? Thank you. So, chemical reactions can produce light. How else can we produce light? Well, we can turn one colored light into another by absorbing one color and making a substance fluoresce or phosphoresce, luminesce. And somewhere in here, I have some tubes of dye stuff. The lamp has gone out. There we go. Which will fluoresce quite nicely. They're taking in ultraviolet light and they're fluorescing all the colors of the rainbow again. So that changing the color of light from one color to another is a way, if you like, of creating light. Now, all sorts of materials emit that kind of light. And let me just show you one, which is of some interest, perhaps. This is a rod of man-made ruby, and if I irradiate it with this ultraviolet lamp and point it right at the camera, I think you should be able to see that it fluoresces quite nicely. If I take the lamp away, you can see that the fluorescence has gone. If I irradiate it again, you can see the red fluorescence from this ruby sample. Now, all of those examples of creating light were creating what's called a spontaneous emission, spontaneous light. And we need to explain stimulated emission. So let's try and see the difference between those two using a very simple analogy. If I have a ball here, if I put this ball at the top of this hill and let go, the ball has potential energy and it can be turned into kinetic energy and the ball will roll downhill. That's a spontaneous process. If I put the ball at the bottom of the hill, you all know that it's not going to, of its own accord, go up to the top of the hill. That would be silly. It can't do that because it has no driving force. There's no motive power there to take it up. But if I have something which has motive power, like this car, then, with any luck, I should be able to drive it up to the top of the hill. Now we'll see how clever I am at doing this. It just about gets there if we persevere, and I'm not very good at steering it, so we'll help it a little. Did we get it there? Yes. Now it has two choices. It can freewheel down the hill, just as the ball did. Let's see that. Good. Of its own accord. That is spontaneous, right? Now let's see if we can get it up the hill again. I passed my driving test with the army, you'll be pleased to hear. So it's just about going to get there. Right. Now, all I want to show you is that, of course, I had to drive it up the hill. I can now have the choice, as you would do in your car, of driving it back down the hill. Thank you, Bryson. That simple analogy is just to show you that when an atom or molecule is excited, it has two choices in terms of losing its energy. It can do it spontaneously, and all of the emission we saw up till now has been spontaneous, or the exact opposite of the absorption process is stimulated emission. Light drives it back downhill again and creates more light. Now, we're familiar with the one process driven by light, the process of absorption, because we see it all around us. Would you like to stand up for me, please, and tell me your name? Sarah. Good. Sarah's wearing a red cardigan. Now, why does it look red? It's red because white light from these light sources is impinging on the cardigan, striking the cardigan. All colors of the rainbow except red are being absorbed by the cardigan, and the red light is being reflected off, and we see it as red. That's an absorption process. But stimulated emission is just the exact opposite of absorption. So why do we not see stimulated emission from her cardigan? Why isn't she lasing like a red beacon over there? Well, let me try and explain why. Thank you, Sarah. You can sit down. It's all to do, really, with where the atoms and molecules are normally, what state they're in. And we can explain that quite simply. With their electrons in the normal positions, the lowest energy position, you find most of the atoms and molecules in this room would be in that state. So we've put all of the atoms in this state, and just to show there is a possibility of some being in the excited state, we'll allow just one to be up there. Now, when light shines on this system, all of these absorb and go up over, and we should see that in just a minute. There's the arrow. That's the absorption process. There's only one there to come down, so we really don't see that. We see absorption because all of the atoms and molecules start out in this level. If we wanted to see stimulated emission, we would simply have to arrange that more of the atoms were in the excited state than were in the ground state. And so if we turn this diagram over, that is what we need to achieve in order to see stimulated emission. We need a population inversion, a population which is bigger in the excited state than it is in the ground state. Well, now, how do we achieve this population inversion? The answer, I think, we can illustrate with reference to this delightful model that Bippin and Bryson have made for us. Here's the normal energy state of the atom or molecule. And the level of water in there, the amount of water in there, represents the population. So we're starting out in a situation where all of the water is in the lower level. We have none in the top at all. Now we switch on our light, and we can start to pump water optically from there to there. Whoops. But as soon as we get a population here, the stimulated emission process starts. We start to pump it back down again. And the rate of pumping, as you can see from these tubes, depends on the level. The higher the level here, the faster the pumping back down again. The lower the level there, the slower will be the pumping from here to here. What happens in a situation like that, I think we shall have achieved very shortly, is that now, just about now, the level here is the same as the level there. So the pumping from here to here, the stimulated emission, has the same rate as the pumping from there to there, the absorption. So we don't see any change in the water levels, we don't see any change in the populations, we see neither stimulated emission nor absorption. That's called saturation. And we've learned a painful lesson. You can't make a laser optically pumped on just a two-level system. All you get is saturation. What we need, really, if we look at this diagram, is a third level. We need what's called a reservoir level, and we have on our model here a reservoir level, there. And if I open this stopcock here, we can drain off some of this level into that. Now this one isn't connected to anything at the moment, and so there's no stimulated emission from there at the moment. We're simply still maintaining populations here, but because this one is draining off, we can actually get a bigger population there than is there. We can achieve a population inversion. But much more easily we can achieve a population inversion if we have a fourth level. Because as soon as we get any water in this tank at all, we have no water in that tank, we've got a population inversion, which is what we want in order to get stimulated emission. So an optically pumped system requires at least 3, if not 4 levels. And a 4-level system will work better than a 3-level system. Now, what happens when you get the molecules excited? One of the things that can happen is that this level can emit spontaneous emission. That's just a fluorescence, and I've put it in blue on this diagram. What we want to be able to achieve is that we stimulate emission from the reservoir level down to the 4th level. That would make our laser. Now, how can I make that happen? Well, I'm going to show you in just a minute. Here is my reservoir level, here is my 4th level, and if I can trigger this to emit all at once, I should be able to get a laser. Let's see if I can do this. There we go. All of the water suddenly went from there to there. That simulated a laser pulse. Now I think we should see that for real, and if we go downstairs to a krypton ion laser which is being operated there, we'll be able to see, and you can see it now here, blue fluorescence from a krypton ion plasma tube which is being excited electrically. We have prevented this stimulated emission from occurring, so all we're seeing is spontaneous fluorescence from the first 2 levels. Now if we uncover a pair of mirrors in this laser, you can now see quite clearly the red laser light, the red stimulated emission, which is coming between these 2 levels. So we can stimulate emission quite readily from such 3-4 level systems. What kind of materials can give us those reservoir states which we can make into lasers? Well, I already showed you one of them, and here is another. This is ruby, man-made ruby. This is a substance called neodymium, which is in glass, or in this case in a crystal, yttrium, aluminium, garnet, and they make very, very efficient lasers indeed. Now then, we need to know how do we trigger this stimulated emission? How do we make the molecules give up their energy all at once? To try and show you that, we need 8 pre-selected volunteers. In fact, the people sitting in that row there, I think, if you look under your seats, you should find some boxing gloves. And I'd like you all to put the boxing gloves on your right hands. You'd find it difficult to put it on any other hand, perhaps. And when you've got them on, will you all stand up, please? I won't ask all your names, but the one on the end is important. So can I have your name, please?
Yeah.
Sorry?
Claire.
Claire, right. Now, will you all turn and face that way, please? Right. Now, these are not children, young people. These are atoms in a crystal. And if I excite them, they signal that they've been excited by putting their right hands in the air. So you've all been excited. Put your hands in the air, please. There we go. Now then, what can happen when they're excited? Claire can simulate a spontaneous emission process if she just drops her hand back down to her side. Right? Do that, please. Right. Now, that didn't do anything, did it? It didn't achieve any effect whatsoever. And that's called a loss mechanism. We've lost that photon. It hasn't done any good. Let's excite you again. Can we have you up and excited? Now I'm going to tell you, if you drop your hand forward, and don't do it yet, you will strike the atom in front. When you atoms feel you're being struck from behind, you strike the one in front of you, please, all right? Let's see if we can get that to work now, starting with Claire. Now. Right, that was all right, but you didn't do it terribly vigorously. Just rest your hand on the shoulders of the one in front. That's where I want you to end up. Let's do it again, shall we? Now you're all excited again. Put your hands right in the air. Now, with a bit of vim and vigor, Claire is going to excite her neighbor in front. Right now. Quick, 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 quick. That's it. You perhaps get the point that a spontaneous process triggered off a stimulated process, another stimulated process, another stimulated process. And along that line, we got some gain, some amplification. Thank you all very much. I suggest you take them off now in case you feel inclined to wallop your neighbor again. Thank you. Good. Now, this is such a crucial concept, this concept of amplification, that I'd like to illustrate it some more. So I need another volunteer. Who haven't I used yet? Would you like to come out? You look suitably sized. Would you go around the front this way, please? And what I'd like you to do is just crouch down in front of this little model here. These are a special set of dominoes, and I want you to start with the small... Don't touch it yet. Start with the smallest one. And when I give you the signal, perhaps you could just crouch right down at the front. So there we go. Just push it forward when I say go, and we'll see what happens. Ready, steady, go. Oh, it failed. I have to give it some help. There we go. All right, I had to assist it. What you saw then was, if you could hand me that biggest one from the back there, we started out with this small domino, and by the end we were knocking down this big domino. So we had amplified the signal as we went along. Now you notice it turned the corner, didn't it? Yes. So I cheated, didn't I? I actually acted like a mirror. I was just like a mirror making the light go back along the same direction. Okay? Thank you very much. You can go back to your seat now. If you think about the atoms in a crystal, that process of amplification could occur in many, many different directions, because the atoms are so close together. In any direction you could get gain, you could get amplification. And to make a laser, we want to make the amplification occur in a specific direction. And we can do that by a trick which I'm now going to illustrate using a sound analogy. So here we have a microphone, and here we have two loudspeakers, and I'm going to make, if I can, not a laser, but a saser, a sound analog of a laser. Now I need two volunteers to help me with this. Who would like to be volunteers? Can I have you two right in the front, please? Would you like to come out? And that's it. And your name is?
Emma.
Emma, and?
Chris.
Chris. Chris, would you like to go to that end, Emma to that end? You'll find two pieces of card there. I want you to pick them up, please, and place them on this bench, just like so. So the corner is right on the mark there. That's fine. Now, all you have to do to make this saser work is to pick up the piece of card, and with any luck we should hear an amplified signal. Put it right up. There we go. You hear it? Now take it back down again. Stops. Lift it up again. Now, all these pieces of card are doing is acting as reflectors, and so we've made what we call a cavity, which is amplifying this sound. Thank you very much. You can go back to your seats now. Thank you for your help. Now, a laser works in exactly the same way, except it doesn't use sound waves, it uses light, and in order to make the cavity that work there, we have mirrors. So let me just illustrate that here. Here is a ruby rod. Here are some atoms undergoing stimulated emission. There is a totally reflecting mirror, which bounces the light back. Here is a mirror which partially reflects. So when the light gets strong enough, it will actually emerge through this partially reflecting mirror, as you will see now. So all we need to make a laser is very simple. We need a laser medium, which might be a ruby rod. We need some mirrors. We need some way of exciting the lasing medium, and very little else. This is a ruby laser which was used by one of the previous directors of the Royal Institution, Sir George Porter, and you can see in it the ruby rod. That's the lasing medium. Here is a flash lamp which is used to excite the ruby rod, so it's an optically pumped laser. At the end here we have a completely reflecting mirror, and at the other end here we have a partially transmitting mirror to let the light out when it has built up enough. So that's really all you need for a laser. That laser was based upon the first working laser, which was made 27 years ago by Theodore Maiman. And here we see how he did it, almost the same. There's the ruby rod. In this case, he wrapped the flash lamp around completely. And there we see the flash lamp wrapped around. And then he put a mirror around that to focus all of the light from the flash lamp onto the ruby rod. And when you fire the flash lamp, you see a pulse of red laser light. Now, I thought it'd be fun if we made a laser work here in front of you, and I will need somebody to help me do this. Let me think. Would you like to come down, please, with the hat on? What's your name, please? Gaia. Gaia, if you stand beside Bryson over there, let me show you again with this laser now. It's not a ruby laser. This one has for a lasing medium a dye stuff. So this is just a fluorescent dye. I put it carefully back into the right position. Just I hope to. There we go. Here are two flash tubes which we can fire in the way that you just saw. At this end we have a completely reflecting mirror, and at that end is a partially transmitting, partially reflecting mirror, and we'll see laser light being produced on this white card here. Now, all you have to do, Gaia, is to charge that bank of capacitors up over there to about 15,000 volts, and then when I tell you, press that red knob in, and we'll see a burst of laser light being produced over here. Why don't you do it now? Now, did anyone see that? No? Shall we do it again? Press it again. There we go. You could actually see it, but it's rather difficult because that pulse of light is over in about a microsecond, a millionth of a second. So let's have a look and see what it actually looked like. Thank you very much. You can go back to your seat now. Let's see what it looks like here. Here is the white disk that we just saw. We recorded this. When the laser fires, you will see a burst of red laser light, and also on it you can see some scattered light from the flash lamp. This is the blue light, but that is stimulated emission. We have actually made that system produce laser light for you in front of your eyes. Now, that was a pulsed laser. That produced light in one giant burst. And we can make lasers which produce 1 million watts of power in short pulses. If you use an electrically pumped laser system, a continuously pumped system, you can then make the laser work on only 2 levels because you're electrically pumping it. You can allow the power to dribble out, as it were, all the time, continuously. And so continuous lasers are much lower powered than pulsed lasers of the sort that we've just seen. Now, at this point, I would like somebody to go with Professor Thomas, who's waiting for us here, down to the theatre below, because we want to see some real lasers. You look like a likely candidate. Can I have your name, please? Benjamin. Benjamin, will you go with Professor Thomas
come with me,
down
Benjamin.
to the other theatre, and we'll join you later in just a minute. Lasers come in all shapes and sizes. Big ones, little ones. Let me show you one of the smallest around. This one is Chinese. It operates on just flashlight batteries. This is just like a camera flash, the assembly, but it really is quite a powerful laser. It's an infrared laser. It works in the infrared invisible part of the spectrum. And to make it operate, I simply have to charge up the batteries. And I have a piece of paper here. You can't see the infrared beam, but when I fire it, you should be able to see some effect on this piece of paper. You can see that the paper was burned, I hope. Let me do that again just to make sure you see it. There's a rather bigger burn. So that really is quite a powerful little laser. I'm going to switch it off and discharge it on the floor to make it safe. The most spectacular lasers, of course, are the visible lasers because we can see them. And they range in size from this baby laser, which you've seen in use in this theatre before. This is a little helium neon laser. Notice that the color of the discharge, the red spot that you see over there, is exactly the same color as the neon tube that I discharged earlier. And I can point to things using this very tiny half milliwatt laser. This is quite safe to use anywhere because it will not damage your eyes. The laser we have, the big brother of that little helium neon laser, is an argon ion laser, for example. We have a 50 milliwatt argon ion laser here. This one we have to be rather more careful with. So if I switch on the beam, all you can see at the moment is the spot of light where the beam strikes this stop here, because there's no scattering material for you to be able to see the actual beam. I can make some scattering material by just discharging an aerosol along, and I think you should be able to see the beam rather nicely there now. You'll see it much better if I put a tank of scattering material, milk will do, in the way. Now you can see the beam quite nicely. And this solid looking chunk of blue-green stuff is actually laser light, which is being scattered into your into the surroundings by the milk particles. And I can make it even prettier, I think. Let's take that out of the way. Can you see, if you look at the spots there now, that there are 2 blue and 2 green spots, that this laser actually produces several different colors of light, and this diffraction grating is splitting those colors up so that we can see the individual colors there. Now, that's a 50 milliwatt laser, and we have to be fairly careful with it, continuously electrically pumped. I am now going to show you again a rather more powerful 4-watt laser, and so we have to take even more safety precautions with this one. And so that laser, the 4-watt laser, which is 8,000 times more powerful than this little pointer that we have here, for safety reasons is housed in the theatre below us, the Bernard Sunley Theatre, where Professor Thomas and our volunteer went to a short while ago. So let's see if we can join them now down in the theatre, and we can see, I think, the krypton ion laser down there. John, over to you.
We've arrived safely, David, and I'm going to ask Benjamin very shortly to switch on the laser. Go ahead, Benjamin. Yeah? Yes, pull it. That's it.
Now, Benjamin has switched on this krypton ion laser. You can see the beam traveling across the floor of the theatre below us. It then strikes a mirror on the wall, is diverted up over onto the ceiling of the theatre below, and is now emerging up through this pipe, through this plastic pipe which protects the audience here, and is then being diverted over my head onto the screen behind you. And you can see several different colored red spots there, which are different colors. In fact, they're different colors produced by the krypton ion laser. I think we should ask them to switch off the laser if they haven't already done so, and to stay down below, because we're going to need them again in just a little while. It's very easy to make lasers operate in the infrared part of the spectrum. We can't see infrared radiation, but we can show very easily that it can have an effect. This is a carbon dioxide laser, quite powerful and quite dangerous for many reasons. We have to be rather careful with this, so that the beam coming from this laser is stopped on this metal plate, and there's a protective pipe put in place so nobody can accidentally get in the way. Now I'm going to remove that pipe and turn on the beam. Now you can't see anything, but just to show you there really is a laser beam there, I'm going to put this balloon in there, and off it goes. And to give you even more indication that there is a powerful, usable laser beam here, I have a piece of wood, and if I put it in position, can you see that the wood will burn quite nicely? And if I were very clever, I could steer that and write my name, but I'm not very clever, so I'll not do that. Now, infrared photons don't carry a great deal of energy compared with visible light, but if we went to the other side of the visible, to ultraviolet, ultraviolet light carries a lot of energy. So if we could make an invisible laser with ultraviolet light, it really would be very powerful indeed. And again, for safety reasons, downstairs we have a so-called excimer laser, which is an ultraviolet laser, and I'm going to ask Professor Thomas and Benjamin to meet Dr. Anita Jones, who will show us the excimer laser. John.
Well, Dr. Anita Jones is standing next to the excimer laser. Let me point out that the black aperture to which she's pointing is where the beam is going to come out from, and it'll strike the prism and then be deflected onto a lens and then brought to a focus on that metal plate. We better put our goggles on, Benjamin and I, because this is a very powerful beam, and then Anita will, when she's ready, switch it on. There it is.
Now what you're actually seeing there is the light, the ultraviolet light from this laser, being focused onto a metal plate, just in front of a metal plate. The laser is powerful enough to etch off, to remove the metal surface, and is also causing the air in front of the plate to ionize. Electrons are being removed from the molecules of the air, leaving positive ions. It's just like a miniature lightning flash which is being produced in the air in front of the metal plate. You can see how immensely powerful those lasers are. They have enormous uses because they can break any known chemical bond. Any material you put in front of that laser will be destroyed, not because of heat, just because of the light, the ultraviolet light intensity which is there. And we're going to meet lasers of that type in future lectures. Thank you very much down below. Professor Thomas and the volunteer can now return to the theatre upstairs. Ultraviolet is very, very energetic, but what is more energetic than ultraviolet? If we look on our spectrum, we see that we would come to the X-ray region of the spectrum to higher energies than the ultraviolet. So if we could make a laser work in the X-ray region, we would have a very, very devastating source of power. But to create stimulated emission in the X-ray region, you've got to put a lot of energy in. And one of the ways of doing it is shown here. It has been proposed that by exploding a thermonuclear device, you could make enough X-rays that you could get stimulated emission and an X-ray weapon. That kind of stimulated emission is not going to be terribly practical for most of us, or certainly not used in the laboratory. I want to talk about the properties of laser light, but before I do so, let me just show you that visible lasers and ultraviolet lasers are generally more useful than infrared lasers, but infrared lasers are the easiest ones to make. Because they're very powerful, we can use some special properties of crystals to turn infrared light into visible light, or visible light into ultraviolet light. Crystals might be, for example, urea, which Professor Thomas talked about. In this case, it's a rather different crystal. This is a little, another miniature Chinese laser. You can see it's housed in a rather attractive box, and it's producing infrared light. But there's a crystal at the front of this box which has the capacity to make the second harmonic of the light. Second harmonic just means twice the frequency, half the wavelength. So we turn infrared light in this laser into visible light, and if you look carefully as the laser fires, you'll see a burst of green light being produced in this scattering medium. So the power of lasers is useful to turn one color light into another color light. Now, what are the properties of laser light which are most useful? What makes laser light different from ordinary light? First of all, the power. Let's look at a carbon dioxide laser being used in industry to cut very intricate shapes out of metal. Here's the tip of a carbon dioxide laser. When it fires, you will see it very readily, very easily cuts through quite thick metal and makes a very, very intricate pattern. You'd find it extremely difficult to make those cuts by any normal technique. The laser does it very easily, is easily steered, and this technique is very, very widely used in industry to make intricate jigs and templates. The same kind of laser, very powerful carbon dioxide laser, can be used to cut through quite thick material. This is concrete, and you can see the laser punching a hole quite nicely through a large piece of concrete. Here's another material, solid material being easily cut through with a carbon dioxide laser. And finally, we see the laser going through a piece of metal, just as though it was going through a breakfast cereal. It really is quite easy for that to happen. So the power of lasers is something which is very important. Another possible use of lasers is that we can make them have very, very narrow, very pure color, very narrow band of frequencies. The argon ion laser produces blue-green light, as we saw. So anything red will absorb that light with, we hope, an obvious result. The light, and remember it is just light, there's no heat there, is absorbed by the material in the balloon, causing the balloon to pop. Now we've got a red balloon inside a different colored balloon, and with any luck we should be able to burst just the red balloon. That's because the laser is tuned to the absorption band of the red dye. Now, we can make some special lasers which are very, very narrow in their color of light, the range of frequencies that are there. To illustrate that, I'd like to use again a sound analogy, because we can do this rather nicely. This is a tube which will have a gas flame coming from it, which we'll see in just a minute when Bryson lights it. There we are. What we have here is a tube in which we're burning gas, and if Bryson produces a sound wave inside that tube, then the variation in pressure caused by the sound wave will appear, because you will be able to see different lengths of flames. And the only requirement that the sound wave can operate in that tube is that, thinking of the wavelength, there have to be a whole number of half wavelengths in the tube. Now there's one example. If we change the frequency, we'll get to another. So there are a whole range of different waves which can be accommodated inside this tube, which is like a laser cavity. In the cavity, of course, it is light waves which are present, and there are several different frequencies which can be accommodated inside the laser cavity. So the laser can produce light in several different modes, as we call them. If you could make the laser work on only just one mode, then the frequency would be very, very precisely defined. And there are tricks, there are ways of doing that, making single mode lasers. Now, to try to illustrate how pure that radiation can be coming from a single mode laser, let's look at our spectrum again, from the red through to the violet. Now imagine that spectrum is distributed right around the circumference of the Earth. There are single-mode lasers available which correspond to just 1 centimeter of that distance. 1 centimeter out of the whole circumference of the Earth is the equivalent from a single-mode laser. So they can be very, very pure in color, and they have many uses, as we'll see tomorrow. What other special features does a laser have? Well, ordinary pair of sunglasses here. I'm sure they don't suit me, but just want to illustrate that they are sunglasses. If I turn on this argon laser again, let me illustrate a special feature. Do we have the tank? Perhaps we can do it this way. If I put the sunglasses in front of the laser beam in this position, you can see the beam still comes through. We'll perhaps see that better if we have the tank of Ludox. There we go. Now I think you can see the beam being transmitted quite nicely. All I'm now going to do is turn those sunglasses round through 90 degrees, and when I get to about that position, you see that the beam is extinguished. So do that again. I go from there, round to there, and the beam is extinguished. Now, that tells us some things about both the sunglasses and the laser. Light, you know, is just an oscillating wave. So here's a wave. And the sunglasses act just like a gate. If the gate is in that position, and this is the wave, then the wave goes through quite nicely. But if the gate is in that position, then the wave can't get through. And that's all that you saw there. Those Polaroid sunglasses are really pretty good. And it also tells you that the light coming from the laser is like one single wave where all of the electric oscillations are in the same direction. So it's a plane polarized light. Now, it's plane polarized not because of any special way that the light is created in the cavity. It's plane polarized because the plasma tube, which is used, has windows at the end which are cut at a very special angle. They cut at what is called Brewster's angle, and it's the Brewster angled end windows which give you the plane polarized light. But nevertheless, plane polarized light is so useful that it's an important property of laser radiation. Now, there's one further thing you can make lasers do. You can make them give incredibly short pulses of light. The world record at the moment stands at something like 10 femtoseconds. Femto means 1,000th of 1 millionth of 1 millionth of a second. Pulse that long is just 5 wavelengths long. So when you make a 10 femtosecond pulse, you've got just 5 wavelengths traveling through space. And I find that quite remarkable. Why would you want to make a laser pulse which is so short? Well, I'll try and illustrate that with a nice messy model which Bryson has rigged up for us. We use pulses of light to take snapshots in time of events which are in fact continuous. Every time you take a photograph with a flash gun, you are freezing an event by just looking at that point in time when the light is on. Let's see what we can do to freeze a continuous event by using a pulsed light source. What we're going to get from this device is a jet of water, which we hope will be largely caught in this tank over here. But I'm going to stand at this end just in case it isn't. There we go. Now, we're going to make the end of the nozzle vibrate. Like that, and you really don't see anything very spectacular, do you? Because we're looking at it in continuous light. But now, if we look at it using a pulsed light source, let's see what we can see. If you look at the screen, and we get the frequency just right, can you all see that what the jet actually looks like is a standing sine wave? And if we change the frequency a little, we can make it go forwards. And if we change it back, we can be very clever and make the water appear to go back into the nozzle. What we're doing is taking a series of snapshots in time and interrogating, looking at events which are happening in this case on a time scale of milliseconds, thousandth of a second, through to millionths of a second. Okay, I think that'll do quite nicely. Here we go. Yeah. Now, I've told you we can make lasers which operate on a time scale of many, many orders of magnitude faster than that. Why would we need to do that? Well, the answer is to look at molecules moving, not water moving, but molecules moving. Here's a molecule we happen to be quite interested in. When that molecule is in a fluid, it rotates like this. Just rotates round and round. And it takes about 1/1,000,000th of a second for that rotation to occur. And so if I want to see that motion, I have to make pulses of light, just as we did there, but here pulses of light which are shorter than the motion I'm trying to look at. And so I have to be able to make extremely short laser pulses in order to interrogate that kind of motion. Well, one last thing really that I would like to show you, a last property of light which we will use in the next two lectures. And that is that light travels in straight lines, and laser light is beautifully formed in a fine pencil. We've seen several examples of that today. That means that the light can be very easily focused and very easily steered down a fiber. We can get light into fibers and then use them for all sorts of purposes. Now, what we have here is a bundle of fibers, 10,000 fibers, all strapped together, and we're passing down this bundle of fibers now some laser light, and you can see the laser beam over yonder. Now, watch the end of this bundle of fibers, please, because what I'm going to do is to very inexpertly steer it. Whoops. There we go. There we go. There we go. I can steer it quite nicely there now. Now, this bundle of fibers has a lot of use in medicine, and we're going to see a real expert actually operate one of these things in lecture 6. So what have I told you today? I've told you about how we make a laser, what a laser is, what makes laser light so special compared with ordinary light sources, just a few of the properties. What we're going to talk about tomorrow is how we can use lasers in the everyday world around us. So we'll see lots of examples of lasers in action. Now, I would like some of you to take home souvenirs of today's lectures. And unfortunately, I can't really give you all a laser to take home. No way of doing that at all. What I can do, perhaps, is to give you all a light stick to take home as a souvenir. but I'm going to spoil things by making you operate them before you leave. Make sure you all catch them, some at the front too, right? Anybody not got one? I don't believe that. Do you believe that? I've just given 300 out. There must be... Fine. I think we're almost got to the point that we've got enough, right? When I give the signal, which marks the end of the lecture, I want you all to break them. You see, I've saved the biggest one for myself. Will you now do that? Thank you all very much indeed.